with automotive qualified versions. We are strongly focusing on higher reliability applications. First of all, I'd like to distinguish and give you a brief overview about the timing devices, which are crystal based. There are other timing devices, more mechanical, but basically recently pretty much all the timing devices are based on somewhat crystals, and they may be categorized as passive parts or active parts. Today we're going to talk about the crystal units, which is a truly passive product. And as you can see, they are basically meant to produce a very stable sine wave output signal, but they need a specific circuits in order to work. And similar to tuning forks, which is a little bit lower frequency and lower power consumpting, actually two-terminal device, there are also some which are called the thermistor crystals that are basically same as the crystal resonators, but it has additional temperature sensor in order to improve the temperature stability. Then are there the active parts, which are, for example, the TSXOs, the temperature compensated crystal oscillators, that are actually very stable. They're providing a very stable, very low ppm output, and they're altering the wave signal as you like. And this one of the specific formats is the clock oscillators, which all of these have an embedded IC that is making some waveforming and some compensation, and they output, for example, the clock oscillator square wave signal. Now today we're going to talk about the crystal units, or the crystal resonators, in other words. What are the crystal resonators? Actually, these are piezoelectric quartz crystals, which is not really a groundbreaking technology. This has been on the market for a long time. This is a very specific, very simple, artificially grown, actually a quartz crystal. So it's basically a silicium oxide or dioxide that functions as a mechanical resonator. So it's an electric circuit, but this particular piece of the circuit, the heart, which provides the heartbeat of all the electronics and communication signals, are actually a mechanical resonator. Why they are very special? Actually, I highlighted here that they are very high stability and adjustment free, and basically can serve in a broad range of applications because they are quite small and very easy to work with. So basically everywhere in modern electronics they are utilized. In terms of the construction, you can see here basically an exploded view. The heart of the device is the quartz blank. So here you can see that it's a very thin, actually, quartz crystal cut with two plated electrodes, one on the top, one at the bottom, which are connected via the conductive adhesives to the external terminals, and is packaged in a ceramic base and closed by a lid in order to be able to operate, because there is basically vacuum inside of this device, as there's a physical movement going on in this quartz blank. As you can see here, how it's pretty much vibrating. So that's basically the piezoelectric effect when you apply voltage over these electrodes. In terms of the frequency, it's very straightforward. So we just need to cut a piece and basically set the thickness of that specific blank or specific cut, and that's how we get basically the frequency. It's not a straightforward process, so don't try at home. It's not. You need a very precise equipment to do that. And I'm going to talk about a little bit more what this means, like it's an AT cut and what the fundamental mode is, for example. Now let's look at what the crystal resonators do in works. So by themselves, by a standalone device, they are not able to do that much. That basically they are set to a specific resonance, frequency. So they have a self-resonance frequency where they can be excited very, very easily. And that's their main purpose. They can be very easily excited, and there's a very low power needed, to keep them excited. And that's basically the main role. And as you can see that they need to be placed in a specific circuit. So you need to have like inverting amplifier and some noise filtering. So if there is without the crystal, it's just basically lets through noise and amplifies noise. But if you place the crystal and there is a specific frequency noise, this crystal will actually pick it up and will start to get excited. And will provide basically this excited frequency at a specific gain. It's normally not enough by itself, so we need to have an amplifier circuit that amplifies it. And in the meantime, it also filters out as much as possible the noises so that the output, basically frequency signal, can be utilized and further work with. Now, in terms of if you're working with an application like an MCU or like a communication circuit that needs a specific frequency to be produced and work with, it's basically fairly straightforward to find a capacitor. So there are a lot of application nodes of the MCUs, which are normally have these other circuits built in. That's normally called the Pearson oscillator. And we just need to add a few capacitors, resistor, and the crystal itself. Now, when it comes to the design and selection of the device, most important is probably the package size. So we try to strive, basically, that's the industry standard, to go smaller and smaller with the crystals. It's not a power device, so basically the package is just, the package can be as small as possible. And it's not really emitting any heat, so it can be formalized very efficiently. You need to know what frequency you need, and normally all kinds of application has its basically preferred frequencies, like when it comes to like GPS or GSM or 4G, 5G, and so on. And then you need to know the load capacitance, which will work well with the rest of the circuit. That's a bit challenging, so I will talk about it a little bit more in detail. Then you need to know what frequency stability you would like to achieve, and obviously what temperature range your application is. And some of the long-term reliability. So there are some different type of grade of crystal resonators available. You may consider as well with the power consumption, even though these are very low power consumption devices, but there are specific applications like real-time clocks, which are battery powered and needs very, very low consumption. And also, if you have a wide temperature range, then the frequency stability of the temperature is important. Obviously, the environmental, like vibration, reliability, and so on. So we'll talk about these a little bit more in detail. So starting with the frequency stability, so basically you need to know what the frequency may vary. Normally we define this in ppm, and that's a number which is actually adding up by different ppm values. I'm going to talk about this more in detail. So you need to see, okay, I want 20 megahertz, and let's say like I can allow maximum like plus minus 100, 150, 200 ppms. That's what my application requires. Then you need to know obviously your temperature range. These crystals are all pretty much made of the same material, same type of bare crystals, but depending on the temperature range, the packaging, the external housing and so on, that may be impacted, as well as in order to allow a lower ppm and a higher stability over the temperatures, the cut of these crystals, the bare crystals may be very, very crucial, so they may cost a little bit more. Then the size and packaging, obviously, that's according to your preference. Basically, the smaller the better, we used to say. And yeah, there are some specific aging characteristic which we at Eaton try to keep it very, very low, but these devices may age. That adds additional ppms for the frequency stability. Uh, Similar to this, there are a lot of reliability. So there are some crystals which are meant to work for like aerospace or automotive, and some of them are for consumer electronics. Obviously, there are differences in the cost, and this goes down to the shock and vibration performance, for example, and that also impacts the cost. It normally goes down to the packaging robustness and the qualification testing that has been performed, or certification, specific certifications if it's necessary. Obviously, availability, lead time, supply chain, those are again in some specific market situation things to be considered. In terms of the product size, the good news is that these are fairly straightforward, fairly commoditized. So as you can see, our smallest packages is a 2016, the largest a 5032. Currently, what we see, the most popular ones are the 2016, like in like computing, consumer electronics, and 3225 is probably for like automotive or the higher reliability products. In terms of the part numbering guide, we try to be as straightforward as possible. So when you, let's say, select a product, it's basically starts with an E, like Eaton Electronics, and then the packaging size, you can see we have 4 different codes, and then the product category. So whether it's a crystal or it's a temperature composited oscillator or a tuning fork with a 32.768 kilohertz signal, we have different codes, and then you need to provide the frequency in megahertz, except of the tuning fork, because that's a very straightforward device. And then you need to provide load capacitance or select a load capacitance, which we'll talk about later, and then providing the frequency tolerance and the frequency stability. These are 2 different things which are adding up. We'll talk more later, and we may add some special characters at the end, especially when it comes to like custom devices. How to read the datasheet? What are the most important parameters to consider by your design or by the selection of the device? First of all, you need to know your frequency, the desired frequency you like to achieve. And basically that's mainly depending on the thickness of the crystal blank. Now, sometimes we also add the cutting type. Actually, all the Eaton crystals are 80 cut except for the tuning forks. And here you can see on the graph what the effect of the cutting type and the cutting angles may mean. So this we will talk about the bare crystal that is actually sliced up from a specific angle, and that has a strong influence on the stability of the frequency over the temperature range and the stability on the basically as it gets at the room temperature as well. The AT cut, that so-called AT cut, provides a very good overall performance. So most of the crystals, like 80+%, are made by these specific AT cuts and being utilized. We also refer to what the oscillation mode is. It doesn't really necessary for you to know, it's just for the information. Actually, all Eaton crystals are a fundamental mode. Fundamental mode means that it's kind of like moving in this direction in terms of like kind of like a shear type of mechanical deformation is happening of the domain, basically movements during the excitation. And yeah, there are different ways. So there are very, very special applications or historical applications that may use like a phase shear, or it may be just a flexure or extension in different angles, or the third level harmonics, which is similar to the standard shear, or the fundamental one. It just happens in more multiple layers. So those are very, very specific applications. For us, all are the fundamental mode and AT cut, which normally for the industrial and the automotive applications provides the best performance, overall performance. A few like standard elements of the devices is or the features. The MSL level, you can see it's MSL1, so there's not much issue with that. In terms of ESD, they are slightly sensitive for ESD. You can see they are classified as a human body model level 2, so 2000 to 4000 volt capable. So they are a little bit sensitive for ESD, but not too much. Talking about the operational conditions, so in terms of temperature, as you can see, the operational or the operating temperature range is pretty much the same like the storage temperature range. Since these products are not emitting that much heat and no internal temperature rise, they're pretty much operating in that in basically with the voltage applied in the same conditions as without. What is necessary to be noted is that the temperature stability really depends on the cutting angle. So here you can see like a cutting angle. So this is a bare crystal unit, and depending on the cutting angle and the tolerance of the angle, you may get a differently stable, different ppm, what we call crystal unit. So that basically normally depends on this cutting angle, and normally when we have an application, when we have a crystal rated for like commercial, like 0 to plus 70 degree applications, we don't need to be necessary to be very particular or very precise with the angle. But in case of the higher temperature, wider temperature range like military, you can see minus 55 to 125. There's a huge effect if the cut is not done so much precisely. So normally the higher temperature grade crystals are more precisely cut, but they are also more expensive. All right. Here are a couple of additional ones. One is the equivalent series resistance. So we define the equivalent series resistance of the component according to the equivalent circuit model. So you can see that depending on the frequency range, we may define a different ESR. This level of ESR is actually quite low. So this means that these products are quite high efficiency when it comes to excitation and keeping it in a vibrating state or in an oscillating state. And yeah, that basically goes down to like a little bit of the efficiency. Now another aspect is the insulation resistance. So it's normally not an issue. We just highlight that it's like 500 mega ohm minimum at 100 volt DC. Normally these devices are installed in a very low voltage environment, so like 5 volts and so on. So that's not really an issue with the isolation resistance. Drive level, though, is an important thing to mention, and that's basically how much current we allow and how much basically power we allow through the crystal unit, because you can overdrive them and damage them. So this is pretty much the maximum in microwatts that we actually define. We may specify a specific one, but normally it's as you can see like around 100 200 microwatts. If you drive them a little bit more excessively, they may get broken. I will talk about that a little bit later, and normally you can adjust it with this resistor, the RD. All right. Now comes the interesting part, frequency stability. There is a given initial frequency tolerance, as you can see, that may be like 10 to 50 ppm. That represents basically the frequency tolerance at room temperature, so like 25 Celsius degree. And we also define like a stability over the operating temperature range. I was taking like an automotive grade crystal unit, which may be a plus minus 50 or plus minus 100 ppm. That actually adds to the frequency tolerance, the initial frequency tolerance. And on top of that, to make it more complicated, there is an aging. So these crystal resonators, depending on the the build like quality, they are aging. In the first series especially, so here you can see that it adds a plus minus 3 ppm in the first year, and then it slows down significantly in the coming years. So that's why worst case you need to consider this number and add it to the uh, general frequency tolerance and the operating temperature based frequency stability. All right, talking about the capacitances. So we talk about the load capacitance, you can see on the datasheet, and the shunt capacitance. And you need to provide, so we provide how much is the shunt capacitance. It's pretty much a given number, like 3 picofarad maximum. We try to minimize that as much as possible, but this is a number that worth to consider. And the load capacitance is something that you actually need to specify. It's a bit challenging in a way that to measure and determine, and sometimes it's recommended. There is a recommended load capacitance by the MCUs, but you may pick as you like. So you can see that it's like 8 to, let's say, 20 picofarad normally, or 6 to 20 picofarad normally, and that basically I will explain a little bit in the coming pages. So here we go. So in terms of the load capacitance and tuning load capacitance, or basically determining how much additional capacitance you need to install, because when you this one is the equivalent circuit of the crystal resonator unit, and what you need to additionally add is normally 2 capacitors, were external capacitors that are helping to set the overall load capacitance as a defined one. So in terms of to get the right frequency with the right initial tolerance, you need to arrive with all the capacitances highlighted here, like the Cin and the straight capacitance and these external capacitances to the level of the load capacitance. So here you can see the formula, and we have some of them are challenging. So like the straight capacitance of the PC board that only can be measured. So when you have some prototypes, you may need to measure, and you may need to adjust these 2 capacitance, like the CD and the CG, and that's how you get to the load capacitance. And that basically includes as well the sometimes the MCU's built-in Pierce oscillators loop capacitance, which sometimes they provide, sometimes not. So it also needs to be considered. So the total loop needs to be considered here. And why is it important? Because that will actually affect the output frequency. So here you can see the Fs. Fs is actually the frequency that the crystal is providing itself, and that actually may be altered by the load capacitance, and that's something which, if you do use the recommended one, then it's going to be pretty much the same as the frequency of the crystal unit, but you may actually tune a little bit the output frequency if you like, altering the load capacitor, the load capacitor, or the load capacitance, which is called actually frequency pooling. So here we arrive to pretty much to the last slide about datasheet explanation. So the actual CD, CG, or basically the overall load capacitance is determining some features and some tunability of the circuit. So here, if you consider a lower, let's say a 6 or 8 picofarad load capacitance, then you actually have a chance to have a easier or higher trim sensitivity. So you may adjust a couple of ppms, a couple of tens of ppms, the frequency, if you intend to do that. That basically means the the output frequency of the oscillator circuit. So you may change. So here you can see just it's a tuning fork, and then how we set it, let's say 12.5 picofarad. That's the recommended one, and then you are actually at like a zero deviation. So that's how we tune the device, or that's the recommended one. But if you would like to alter a little bit, you can actually select a little bit lower or higher load capacitance. So you can change a little bit. Um, you can change a little bit the actual frequency. Normally, we define it as a trim sensitivity, so we have basically like 20 decibels per picofarad or something like that. At a lower picofarad tuned products, the trim sensitivity is higher. So with a little bit of a change, you achieve a much better or much larger ppm. That concerns basically the stability. But also this is lower capacitance tuned, basically crystals are a bit better in terms of efficiency. We don't talk about huge efficiency improvements, but a couple of percentage for sure. When you select a higher load capacitance, let's say 12 to 20, they arrive with a better ppm stability over the whole like operating range. The effect normally of the tunability is much lower here. So overall, they provide a better ppm stability, but they are a bit lower efficiency as well. The other external component that you need to set is the basically it's a resistance that is helping to set the power for the oscillator, for the crystal. Obviously, if you use a higher resistor, then it provides actually a lower, so better ppm profile. Somewhat, the overall circuit will work a little bit more stable and better stability. But if you are using a lower RD, then actually the startup gets quicker. So the excitation, the frequency stabilization is getting in lower. We talk about here 1 to 2 milliseconds. So it's quick enough, but you can make it quicker, you can make it slower. And obviously, if you allow more currents to flow through the crystal unit, then it will consume more. So using actually higher RD basically results a bit better efficiency. Yeah, obviously, if you let more current through here, you may risk for overrunning this kind of product. All right. So let's see the applications. Normally, in all modern electronic circuits, there are MCUs or all kinds of communication devices that requires specific, very stable frequency. So we focus on this kind of markets, and I brought you a couple of specific examples from like the industrial world. So you can see that they are mainly used in MCUs or all kinds of controllers, sensor devices, but all kinds of microcontroller-based devices, PLCs, industrial controllers, robots, all kinds of circuits, and mainly they are using 8, 16, 32 megahertz, and a couple of pieces per each. Smart metering or IoT devices are also special, and especially in Europe, they are very, very common, very popular. There are two different types of crystal units used. Actually, one of them is a special one. It's called the tuning fork, and the other one is specific, the normal crystal units. So you can see that for all the communication lines and the controls, you need to run the MCU at some specific frequency. So you may need a couple of crystal units, and for the real-time clock backup, you need a tuning fork. The tuning fork, as you can see here, that's a two-terminal device. They are normally a bit smaller than the standard crystal units, and they are different cut. They are very special cut from the crystal, so they are actually they're tuned for the highest efficiency, and they are they're also needs to be very low power consumption, because during the RTC backups especially, there's just normally a coin cell supercaps or a coin cell battery providing for months the power for the real-time clock, and efficiency is very key. So here the basically the micro and nano amperes are basically the range of the power consumption necessary. In terms of automotive, in a modern vehicle, it's about 150 crystal units utilized and used. As you can see, pretty much everywhere in all kinds of areas in the cars, there are some used, especially in infotainment telematics. So obviously for the hands-free, for all the wireless communication and the new connectivity, basically antennas and so on, the V2X or vehicle to everything else communication, it's all wireless and needs basically specific signal frequencies. The advanced driver assistance system, those are probably the second biggest user. Again, a lot of cameras and sensors, they only the specific frequency signals when it comes to the radar or all kinds of wireless detection systems. And then probably the powertrain and safety system. So all these products are using some level of MCUs and communication, wired communication, that needs a clock signal, stable clock signal. A special application is the tire pressure monitoring. This is also normally a wireless communication communication process. Needs again at least a tuning fork and body and security. So they also have a lot of controllers and then communication units which is necessary to be utilized and powered by these kind of devices. So that was it for today. Thank you very much for your attention. And now I'm opening the Q&A session. If you have any questions, feel free to ask. Thank you.
Thank you very much, Akos, for that presentation. That was excellent. I learned a lot about oscillators and timing devices. Very insightful. I see that we have a few questions already coming in. Are you ready to answer some of the questions?